Imagine a librarian in a vast labyrinthine library tasked with organizing every book in existence. The librarian devises a system. Each book is cataloged in a set according to its content. One day, they create a special set called the set of all books that do not mention themselves. The librarian pauses, a flicker of doubt crossing their mind. Does this set's catalog card belong in it? If the set includes itself, it violates its own rule. It must contain only books that do not mention themselves. If it excludes itself, it qualifies for inclusion. The librarian's dilemma is a metaphor for Russell's paradox, a logical contradiction that shook the foundations of mathematics to its core. The paradox asks, can a set contain itself? And what happens if we try to create a set of all sets that do not contain themselves? The answer unravels like a tangled thread, revealing that even the most rigorous systems of thought are not immune to self-destruction. Russell's paradox is not just an abstract puzzle, it is a mirror held to the limits of human logic. It asks, can mathematics ever be fully self-contained, or are there inherent contradictions we cannot resolve? Explanation of the concept. Bertrand Russell formulated the paradox in 1901 while studying the work of German mathematician Gottlob Frege, who sought to ground mathematics in set theory. Frege's basic laws of arithmetic aim to define numbers and arithmetic using sets, a bold project to make mathematics a perfect, unshakable edifice. Russell's question was simple yet devastating. Consider the set of all sets that do not contain themselves. Does this set contain itself? Let's break it down. 1. Define the set. Let R be the set of all sets that do not contain themselves. 2. Assume R contains itself. If R is a member of itself, then by definition it must not contain itself. Contradiction. 3. Assume R does not contain itself. If R does not contain itself, then it satisfies the condition for membership in R. Thus, R must contain itself. Contradiction again. The paradox is a self-referential loop that cannot be resolved within the framework of naive set theory, which allowed unrestricted set creation. The problem stemmed from the comprehension axiom, which stated that any definable collection of objects forms a set. Russell's paradox showed this axiom was flawed. It permitted sets to refer to themselves in ways that led to contradictions. To illustrate with a metaphor, imagine a barber in a village who shaves everyone who does not shave themselves. Does the barber shave himself? If they do, they must not, since they only shave those who don't. If they don't, they must, since they shave everyone who doesn't. The barber's dilemma mirrors Russell's set. Self-reference creates an unresolvable contradiction. The paradox nearly destroyed Frege's life's work. He received Russell's letter outlining the paradox just as his book was going to press. In a postscript, he wrote, "A scientist can hardly meet with anything more undesirable than to have the foundation give way just as the work is finished." Exploration of implications. Russell's paradox did not just shatter Frege's project, it reshaped mathematics itself. 1. The collapse of naive set theory. Naive set theory assumed sets could be defined freely. Russell's paradox exposed that such freedom led to contradictions. Mathematicians realized they needed stricter rules to prevent self-reference and infinite regress. 2. The birth of axiomatic set theory. The crisis led to the development of Zermelo-Fraenkel set theory, ZFC, which introduced axioms to restrict how sets could be formed. For example, axiom of regularity, no set can contain itself. Axiom of separation. Sets cannot be defined using unrestricted comprehension. They must be subsets of existing sets. These axioms created a safety net to prevent paradoxes, but they also acknowledged that mathematics could not be entirely self-contained. 3. The limits of formal systems. The paradox foreshadowed Gödel's incompleteness theorems, segment 12. Just as Russell's set could not be contained, Gödel showed that any formal system powerful enough to describe arithmetic would contain truths it couldn't prove. Both revealed that mathematics is a human construct, imperfect and ever-evolving. 4. The paradox of self-reference. Russell's paradox is a cousin of the liar paradox, segment 12. Both expose the dangers of self-reference in logic. A sentence or set that refers to itself can create contradictions, forcing systems to impose hierarchies or restrictions to stay consistent. 5. Philosophy of mathematics. The paradox sparked debates about the nature of mathematical truth. Is mathematics discovered or invented? Platonists argued that truths exist independently, but Russell's paradox suggested that even these truths could harbor contradictions. Constructivists and formalists redefined mathematics as a game of symbols, acknowledging its human-made limits. 6. Computer science and programming. Russell's paradox lives on in computer science. Languages like Lisp and Haskell use recursion and self-reference carefully to avoid infinite loops. The paradox reminds programmers that even algorithms can fall into logical traps if not constrained. 7. Physics and infinity. The paradox questions our understanding of infinity. In physics, infinities crop up in quantum field theory and cosmology. Just as Russell's set cannot coherently include itself, some infinities may be too large for our theories to handle, requiring renormalization or new frameworks. 8. The comfort of imperfection. The paradox offers a strange reassurance. Perfection is not required. Mathematics thrives despite its limits, just as a library survives even if its cataloging system isn't flawless. The axioms of ZFC are not perfect, but they are sufficient to build most of modern mathematics. 9. The ethical implications of foundations. The paradox challenges the notion of absolute truth. If even mathematics, a field built on logic and rigor, has unresolved contradictions, what does that say about moral or ethical systems? Can any system claim infallibility? 10. The cosmic scale of uncertainty. The paradox mirrors the universe itself. Just as a set cannot consistently define itself, perhaps the universe's laws contain inherent contradictions or limits we have yet to uncover. Transition to the next segment. Russell's paradox asks, can mathematics ever be fully self-contained? The halting problem asks, can a computer ever know what it doesn't know? Imagine a program that determines whether another program will halt. Alan Turing proved this is impossible, the halting problem. Like Russell's paradox, it reveals an inherent limit to knowledge, but this time in computation. Both paradoxes share a common thread, self-reference. Russell's set refers to itself. The halting problem's program evaluates itself. Both show that systems, whether mathematical or computational, cannot fully anticipate or contain their flaws. Russell's paradox shattered the dream of a perfect mathematics. The halting problem shatters the dream of a perfect machine. Together, they remind us that human creations, no matter how elegant, are finite and fallible. As we turn to the halting problem, we shift from the paradox of sets to the paradox of computation. Russell's contradiction was about inclusion. The halting problem is about prediction. Both ask, what can we know, and what must we leave to the unknown? This expansion weaves Russell's paradox into a meditation on mathematics, logic, and human limitation. It avoids bullet points by using narrative and philosophical exploration, maintaining the reflective tone. The transition bridges seamlessly to the halting problem by contrasting foundational mathematical flaws with computational undecidability.